Hello. I'm back with quite a short video, to be honest, because I'm gonna go over the questions that were not already covered in the HL portion of the paper 1 videos I sent out. And also, a little bit of a problem. My source, when they sent me paper 1 for SL, it actually started on question 5 for the short answer. So there's only 2 short answer questions, and question 5 and 6 are questions 4 and 5 in the HL version. And the previous questions, like this one and this one and this one, these are all SL level questions, so I'm pretty sure 1, 2, 3, 4, and 5 from HL are the 5 of the 6 questions in the short answer from the SL. So I'm only missing one. Sorry guys, but that's just how it is. So I'm gonna go through the 3 long answer ones, but of course this one here, I went through in the HL version. There is one little detail though. This last question here is different, so I'll just mention this one real quick. And yeah, so today we're just gonna go through the long answer ones that were not in the HL papers. So here we go. So consider this curve. It has an equation. You want to find the derivative. Easy peasy. We just use your derivative rules. So this is going to be 3x squared minus 2x minus 1. And then we need to find the second derivative. So then that's going to be 6x minus 2. And then it says here we have a local maximum at A. So local maximum basically means that your first derivative is 0 because your tangent gradient should be 0 there. And then we want to find the coordinates of A, and we also need to justify your answer. Okay. So we're gonna equate our first derivative to 0. And then we need to solve this. It's a quadratic, so in paper 1, they're almost always going to be factorable if you need to solve them. 3x squared needs to have 3x times an x, and then the minus 1 constant term needs to have a 1 times a 1, and then we just need to find out where the pluses and minuses go so that we get the minus 2x. So that means that I need a negative 3, so it's going to be negative 1 over here, and I need a plus 1. Okay, so from there, we have our 2 solutions. X is either 1 or the other one, which is negative 1/3. Okay. Now, they're being specific here. They want you to use part A to justify your answer. So that's the second derivative. So what that means is we need to show that this is a maximum by using the second derivative test. So the second derivative test, well, the second derivative tells you the concavity of your function at an x value. So everywhere from here to here, if you plug in your x values into your second derivative, then these are all going to be less than 0 because this is a concave down section on your graph. So to show that something's a maximum, then all we got to do is plug the x value into the second derivative, and if it returns a negative, then that means that your graph is concave down there. Combine that with the fact that we already know the first derivative is 0 there, then it has to be a maximum point. So what we're going to do is we're going to take 1 and negative 1/3, and then you can plug them in for x and then find out which one has a negative value. And then you can kind of see, like, it's obviously this one. And I think they do want the full coordinate of A. So next up, we also need to find out Y. So anyways, okay, let's just do this. 6 times negative 1/3 minus 2 is definitely less than 0. So that means that we have a max at negative 1/3. And then we need to calculate Y. It's a little annoying that they're making you do fraction math, but fine. Negative 1/3 to the power of 3 minus negative 1/3 squared minus 1/3 plus 1. Oh my gosh. Okay, so this is negative 1 over 27 plus 1 over 9 minus 1/3 plus 1. Okay, let's make everything 27. So this is 3 over 27. This is going to be 9 over 27. And this is 27 over 27. And then we have negative 1 plus 3, which is 2, minus 9, which is negative 7, plus 27. So what, like 20 over 27? So your maximum at A is at negative 1/3 and 20 over 27. Okay, next we have an inflection point at B. So same thing, inflection point, it has two requirements. The first requirement is the second derivative needs to be 0 there. Because inflection point basically means that you change concavity. So either you have a negative second derivative and then it changes to a positive one. So this is 0 when we're talking about the second derivative. Or you have a negative because it's concave. Oh wait, I have this positive, then it becomes 0, then it becomes negative, right? This is concave down, this is concave up, or it switches from up to down. So the first requirement is you have, your inflection point has to have a second derivative of 0, and the second requirement is that before and after need to change from positive to negative or vice versa, because there is the other kind of orientation of a graph that would give you a second derivative of 0 that's not an inflection point, and it kind of looks like this. So this has an inflection point of 0. But if you notice, oh wait, hold on. This is fine too. This is negative, right? Concave. This is concave down. And then it goes concave up. So negative and then positive. Okay, that's an inflection point. Whoops. I'm talking about like, so this is another example of an inflection point. Oops. The one I'm talking about looks like this, I think. So you can see that it's concave up before and also after, but if you were to like take the second derivative, it would be 0 here. So an example of this is like y to the power of 4. Or sorry, y is x to the power of 4. So not an inflection. But anyways, that's aside from the point. We just need to solve this. So 6x minus 2 is my second derivative. So solving for x, this is going to be positive 1/3. Okay. And then it says here, find the x coordinate of b. So because it says that we have a point of inflection, because there's only one solution for it being 0, you don't need to justify. If you had to justify, you would take like an interval test. Like you would plug in values of x to the left and to the right of this into the second derivative. And then you would see whether or not it changes signs before and after 1/3. But it tells you it's an inflection, so you don't need to justify it because there's only one answer. Anyways, we found the x coordinate of b. Next up, we have the line L is normal to the curve at this point. Then we need to find the equation of L. So L, right, is a line. So it can follow a... and then they give you the point. So we're just going to use the point gradient form, which is like y minus y1 equals m times x minus x1. And then this is your x1, y1, right? And since like I'm basically only doing 2 questions, I can talk a little bit more about each one. For the longest time, I didn't know where this came from, like when I was in high school, and then I just realized that this is just a rearranged version of the gradient formula, right? Because the gradient formula is the change in y minus the change in x. And as long as you have a fixed point, right? So like, let's say this is x1 and y1. And you know what the slope should be, so you have a fixed slope. Or sorry, gradient. Where I'm from, outside of IB, we call it slope, but... let's say, for example, it's like 1/4, right? And then it doesn't matter what your second coordinate is. If these are like, you know, set in stone, like these are done, because this is a very specific line, then what we can say is that, okay, any other point, which we're just going to call xy, all of these 3 things need to satisfy this equation. And then all they do is they just like rearrange it so that it's like this, because, you know, we like y on one side and then x on the other. So this just comes from, like, if you have these 2 things like set in stone, like this is the line needs to have a slope, it needs to have a point, then this we leave as a generic x and y that goes like here, and then any x and y we plug in here, it has to equal 1/4 when you subtract these coordinates. Again, like these are kind of, the question tells you that they have to happen, right? And you see it gives you a slope. It has to be normal to the curve. So then this is always going to be true if you have a specific slope and a specific point. Anyways, that's enough yapping. Okay, the thing that we are missing, however, is the gradient. We do know that it's normal to this curve at 0, 1. So a normal slope, I'm going to use a perpendicular symbol. So like, let's say that this is the normal slope or gradient. This needs to be the negative reciprocal of the tangent slope. So the tangent slope is y prime, and this is specifically at an x value of 0. Because whatever the graph looks like, you know that there's a point at 0, 1. This has a tangent gradient, and we are trying to find the normal gradient. Okay, so what we're gonna do is find out the derivative at 0. So the derivative at 0 is just -1. So this means that your normal gradient is +1, which means that your equation of your line is y minus 1 equals x, if you were to substitute in all your values. Yeah, and that's it, right? Yeah, not difficult question at all, like straight out of your homework. Okay, and then this one, again, if you want me to go over this in more detail, you should watch the HL long answer video for paper 1, because I went through all from A to E, and then the only difference here is the number. This wants you to find the number of solutions where f is equal to g. So f has a graph that we have already determined right here. So I'm going to copy it. And then we are trying to find out where f equals g, or find out how many times f equals g, so we're finding the intersection between the two graphs. As an SL, another thing that you might have tried to do is you might have tried to equate these two functions. So you made this equal to g of x, except, here, let's go back and find, I forgot what g of x exactly is anyways. Where's g of x? This, right? G of x. Oh yeah, okay. So you might have done this. This is g of x. This is f. So you might have equated them and then multiplied the denominator over. And then if you multiplied it out, you get a cubic function, which is something that you can't solve as an SL. So some people might have been like, okay, I'm gonna equate these, and then I'm gonna have like a quadratic maybe, and then I'm gonna use the discriminant because the discriminant is usually related to the number of solutions, but that's not what you're supposed to do. What you can do, however, is you do have the graph of this, and g is just a quadratic. So they ask you details here about the x-intercepts, the solutions, and even the vertex. And so you can graph it against this graph, and then you'll see how many solutions there are, because you'll see how many intersections there are. So let's see. We have two roots, right? At -1/2 and p is 9/2. So let's go back to this one. So let's say that g is going to be green. So we have a root at -1/2 and at p. So at -1/2, there's a solution that's at least 1. And then 9/2 is like 4.5, right? So it's like somewhere over here. Okay. And then you can look at where the vertex is. So that is in one of your answers in E. Find the y-coordinate of the vertex, which is at -25/4 at two, right? Yeah, axis of symmetry is 2, and then -24/5, that's like pretty down here. Like, that's almost -5. Okay, so your vertex is going to be down here, right? And then if you just quickly sketch your parabola, you get this. So you can see that there's going to be 3 solutions. You're not asked to find out what they are. That's not something that you're expected to know. But there should be 3 solutions if you just sketched them on the same grid semi-accurately. Okay, and then the last one, which looks like probability. So what, we got balls in a bag, buttons in a bag, red and blue balls, buttons, same thing. Okay, let's see. 3 red, 1 blue. When she takes 1 from the bag, she's gonna replace it and add in 1 button of the same color. Okay. Here's the tree diagram. So let's... Okay, so here's the tree diagram, and then let's find P and Q. That's probably what the first question is, but whenever I see a tree diagram, I like immediately try to fill it out. So she replaces it, right? And she adds another one. So there's 3 red, 1 blue. So if you select, the probability of selecting a blue the first time is 1 out of 4. And then if she were to select a blue one, she puts the blue one back, so there's still at least 1. But then she puts another blue one in the bag, so then now there's 2 blue buttons, and then now there's 5 buttons altogether. There's still 3 red buttons because she hasn't changed it if she selected the blue one first, but like we said, there are now 5 buttons altogether from the second blue one that she put in the bag after she picked the first one. Then we need to show that the probability that Francine selects 2 buttons of the same color is 7/10. So there's 2 ways that she can collect or select the same color. She either does a double red or she does a double blue. So the probability of getting 2 reds is 3/4 times 4/5, which is the same as 3/5. The 4s will just divide. And the probability of getting 2 blues is 1/4 times 2/5. And then these will divide or simplify, and that's a 2. So then this is a 1/10. Okay, so the probability of getting the same color is 3/5 plus 1/10. That's basically the same as 6/10 plus 1/10, which is, as they said, 7/10. Okay. Given that Francine selects 2 buttons of the same color, find the probability that she selects 2 red ones. Okay, so it says given, which is immediately a signal or a hint that this is conditional. Conditional. So there is a formula, right? The probability of something happening given event B has happened, then that's just the probability of event B underneath. And then over the top is, well, you need the probability of A happening, but also it needs to all have B happen as well, because you know that B has happened. Okay, so what is this? For us, in this question specifically, we want 2 red given we know that it's the same. So the probability that it's the same is 7/10. That's what they told you. And then now we need to find the probability that you have 2 red and intersection the two buttons you have are the same color. And this is kind of a common type of question with conditional. So think about so here's the probability that they're the same color, right? It's like 7/10. And in intersection, normally they teach you is like the two probabilities overlap a little bit, so then this is their intersection. However, think about where 2 red would belong if you were to draw like a Venn diagram. It makes no sense that there is a part of the 2 red that's outside, because anything that's 2 red is considered is also considered a same 2 of the same color. So this is 2 red. And then the other part of the same, right? This is 2 blue. So in other words, the intersection between 2 red and the same is just the probability of 2 red, because it's a subset of having 2 of the same color. There's no outside part for 2 red. So anyway, so this is the same as the probability of 2 red up top. Okay, with that being said, we do know what the probability of having 2 red is. We calculated it here, right? It was 3/5. So it's 3/5/7/10. Okay, and then you can just multiply by the reciprocal. And then, let's see, these reduce to 2. So what, 6/7? Okay. Given that Francine... Oh yeah. That's the one that we just did. Okay. Now we have a random variable. X is defined as the number of red buttons selected by Francine. Show the probability distribution of X. Okay, so the probability of her selecting no red buttons is 1/10. So they get that from basically saying that she had selected 2 blues, right? So 1/4 times 3/5. Oh wait, no, that's the red one. So 1/4 times 2/5, so double blue, right? This is the same as 1/10. We know what the probability is of getting 2 reds. That is 3/5. And just for the sake of working with fractions, 3/5 is the same as 6/10. Okay. And if you want to find the probability that she gets 1 red, there's 2 ways you can do it, right? You can add these 2 probabilities together, the red and the blue, and then the blue and the red. Or you can just also use the fact that when you have a distribution table, these, right, have to total 1. And if they have to total 1, then this has to be 4/10. Because 1 plus, or sorry, not 4, 7/10. Because this is why I wrote this as 6/10 instead of 3/5, because 6 plus 1 is 7. Oh my god, what am I doing? This needs to be 3. Sorry. There you go. So 1 plus 6 is 7, so this needs to be 3. And then we need to find the expected number of red buttons, so that's easy enough to do. You just multiply your x with your p, and then you add these up. Times. Okay, so what is this? Well, 3 out of 10 plus 12 out of 10. And instead of reducing the 2 and the 10, right? Because I'm adding them anyways, I'm just gonna multiply the 2 with the 6 instead. And then this is 15 out of 10, which is the same as like 1.5, which kind of makes sense, right? On average, she's gonna get 1.5 red buttons. Okay. Francine restarts the process. 3 red, 1 blue, same thing. She selects the buttons as before, but oh, she stops once she gets a blue one, right? So given that the first 2 buttons she selects are red, write down the probability that the next button she selects is blue. So if her first one is red, then that was like 3 out of 4, right? So that's the first one being red. And then the second one being red is 4 out of 5. So that means that for her to finally select a blue one, then now there's 6 buttons, but there's still only 1 blue one. So just be careful. This is just asking strictly for the probability of having the blue one. So it's this answer. These have already happened. They're given. This is kind of a conditional, but we don't use the conditional formula. You just kind of draw a tree diagram. So just be careful. The language is important. If this question asks you for what is the probability that the third one is blue, that would mean that you would have to multiply all of these together. This is saying what's the probability that it's blue given that the first 2 were red. So that's the 1/6. So just be a little careful about the language. Anyways, the probability that she selects the first blue button after n selections is a total of 3 over 56. Find the value of n. Okay. After n selections. Okay. Okay, when you approach these types of questions, it's good to see if there's like a pattern with n. And what you can do is you can just start small. So see what the probability is when n is 1. See what the probability is when n is 2, 3, and so on, until you see a pattern. So if n is 1, then this means that she has selected the blue button right away. So that's 1 out of 6, or sorry, 4. If n is 2, then that means that she first selected the red one, and then she selected the blue one. 3 is red, red, blue. And maybe you can sort of see a pattern appearing with the numbers. So red, 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 and then blue. Okay. Let's just do one more. Honestly, I suck at seeing patterns. So, red, 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 blue. And then, let's see, why don't we simplify fractions and see if anything shows up there. You can probably work with factorials, but as an SL student, maybe you don't need to. So let's see. This is gonna be 3 over 20. This one was 1 over 20. Or sorry, 1 over 4. Let's see, 4's cancel. So you got 3 over 30. And I don't know if there's going to be a pattern this way. I'm trying to avoid using factorials, but maybe we don't have a choice. What's 6 times 7? 42? Maybe I'll leave this as 4 times 5. This is 5 times 6, right? This is 6 times 7. Okay, maybe there's a pattern emerging. And then 4, 4, 5, 5, 6, 6. So then this becomes 3 over 7 times 8. Okay, aside from the very first one, all the numerators are 3, and then the denominator is always just going to be 2 consecutive numbers, right? So this is what I'm trying to do. I'm going to try to relate the number 5, or n, with these two numbers. And I think that if you take a look, this one is always n plus 2, and then this one's always n plus 3, right? If n is 4, then 4 plus 2 is 6, 4 plus 3 is 7, right? This one is n is 3, so 3 plus 2, 3 plus 3. This one is 2 plus 2, 2 plus 3. And then this one here, right? Does it still work? Let's see. Let's see. Why is that one the one that's not nice? So 3 times 4. This is not 3 times 4. And then this is just 3, right? Do they really want you to use factorials? Or is there just a nicer way to do this? Fine. I was trying to avoid this to see if we could do it without factorials, but because I can't recall. I'm not entirely sure that factorials are part of the SL curriculum, but they might be. Well, if you guys do have a non-factorial way of figuring this out, let me know. But, okay, if you take a look, you essentially have factorials here. Notice that your denominator is more or less n factorial, well, n plus 3 factorial. Right? 5 plus 3 is 8. And then it's 8 times 7 times 6 times 5 times 3, or times 4. It always stops at 4. So what that means is that we do want to remove the last 3 times 2 times 1. So 8 times 7 times 6 times 5 times 4 is the same as 8 factorial divided by 3 factorial. Then in the numerator, notice, right, that ignoring the 1, it's just n plus 1 factorial. Right, so this is 4 factorial, 4 times 3, and then there's the 2, 1. Let's see, 5 factorial, right? Plus 1 is 6, 6, 5, 4, 3. But we are missing the last 2 factorials, so we're gonna divide it out like that. Again, if you're not sure what I mean, 8 factorial, 3 factorial. If you divide 2 factorials, the smaller one will cancel with the factors in the larger one. Because like this is 8, 5, 8, 7, 6, 5, 4, 3, 2, 1. This is 3, 2, 1. And you see, because I only want these, I get rid of the first 3, so then I divide by 3. Okay, but here's the formula for the probability of selecting after n buttons. Of course, it's pretty ugly, and we are going to simplify this. So this is n plus 1 factorial over 2 factorial, and then you multiply by the reciprocal, 3 factorial over n plus 3 factorial right here. Okay. And then certain things cancel out. This 2 factorial is going to cancel out with the 2 times 1 in here, so that just leaves a 3. And the n plus 1 is going to cancel out with the factorial in here, and it's going to leave you with the n plus 3, and then the next one, the n plus 2, which is what we said earlier. What the? Okay, so then your formula becomes 3 over n plus 3 n times 2. Hey, this is kind of what we had earlier. And then this is a 3, because all of these had 3. Except for this one. Wait. Maybe I was onto something, but this was throwing me off. If this is n plus 1... Or sorry, we said it was n plus 2 and then n plus 3, right? In other words, this should have been This should have been 3 times 4, which is 12. Oh, yeah, there's always just a 3 on top. It's just that 3 over 12 reduces to 1 over 4. Oh, okay. We could have done it the first way too. Anyways. I think that would have been a little tough to recognize in the middle of an exam. But okay, this is equal to 3 over 56. So this is equal to 3 over 56. Then obviously that means that these have to be equal. So multiplying it out, this is your equation, which means that this is something that you need to solve. This is factorable because it's paper 1. And then there's only one solution, the positive one, so there you go. Okay, done. Still took me 46 minutes because I did take a little bit more time explaining certain things, and yeah, this one took a little bit more time because I didn't want to use factorials for y'all SL kids watching. Yeah, overall it's not bad. I think literally all of these questions are questions that you should have more or less done as practice exams, whatever. So super easy. Obviously there's going to be some tougher ones because we need a way to determine who's a 6 and who's a 7. But thank you for watching. Sorry I couldn't do the missing short answer question because there is one that was not on the HL exam, and I guess we'll never know. Okay, see you guys later.